Welcome everyone. In this project, we explore how deep reinforcement learning algorithms are working for robot locomotion, especially how we can employ them in real-world setups. Our project focus on measure how adaptive and robust are those algorithms that we chosen to study in terms of deploying the algorithm on a different robot that was originally used. So we got a Unitary Go 2 robot that was recently bought to No Magic Lab. And on the RL algorithm that we chosen, we performed all the way, all the road to deploy the algorithm and to study them on the new robot, to analyze performance and especially the strengths and weaknesses of those algorithms. Because such a way led us to reflect on real-world challenges in applying RL and also to analyze the algorithm from the other perspective. So what was our key steps? We have chosen algorithm that was basing on only intrinsic observations of the robot. And we had to reproduce the simulations. We wanted to reproduce the simulations that was original, and after that create a simulation of our new robot on those algorithms. After that, prepare a repository with code to implement changes, to create code that was compatible with our new robot, to rewrite communication protocols, which was a time-consuming task, and everything to perform the forward locomotion on the real robot. So our work was from the one side engineering and from the second side extensive experiments to analyze hyperparameters and understand what is going under those algorithms. So despite the forward locomotion is a complex task, we managed to perform almost all key steps of our plan. We deployed the APRL algorithm on the real robot and we got basic forward locomotion. Due to the time constraints, the Dr. Ireka paper requires further work. However, a lot have been done. A lot of insights that we gave to both papers are nice and will help future work. And what one more we bring is the code, the setup that can be used for future work with those algorithms. We'll now tell you briefly about the papers that we chose. The first one, APRL, is an algorithm that works on a robot, on a real robot, and it's without pre-training. It's using the robot observations from the very beginning of the training to continuously improve the policy and to get the robot walking in time without weird behavior as you see here, but through safe exploration of the movement. And this is done among others by the adaptive threshold, which is performed by learning which states are known and which states are unknown and letting the robot explore more in the known states and narrowing it down in the states that are not as known. So this is an algorithm that sets it apart from all the sim-to-real algorithms that require a lot of work to adapt simulation, which is not ideal always, to a real-world setup.
So domain randomization Eureka is an algorithm that automates sim-to-real transfer process for robots by leveraging large language models. It autonomously generates reward functions and domain randomization parameters for more robust policies, eliminating the need for manual tuning. Mm, This approach enables seamless deployment of policies trained in simulation. Oh yeah, thanks. In simulation to real-world environments, as demonstrated by quadruped robot balancing on yoga ball without additional tuning. We use it for the purpose of performing the task of forward locomotion.
Okay, now I will tell you about effects of our work with APRL. I will start talking about it. Firstly, we rewrite the repository to get the simulation on the Go1 to simply reproduce the results, and on Go2 to do the same on the another model. That was time-consuming task. We succeeded in it, as you see on both um, graphs. The velocity is not bad. It's moving fast, and the better metrics of Go2, we think that comes from the better model, but it's also the better robot. We have also short films for you with movement. It's nice moment to strengthen the fact that what we see in simulation is not the mirror of what we see in real world. Like all the simulations that we do give us nice insights into the algorithms, help us to understand how it is working, but this is not the same as deploying it in the real world, where the parameters of physics are somehow not the same. So we have prepared the code for the real deployment of the algorithm, and there were a lot of steps and issues that we encountered, and we'll talk about a couple of them later. But now I want to show you the movement that we got. So as you see, we changed the floor, and we'll talk about later to the hole. And the robot, this is a film after a couple of minutes of training. So after a few falls, after going in different directions, it learned to be stable in the right position, in the position that is safe for it. And it is exploring in the right way. It is not turning left or right. Now it is slow, as you see, but what it is performing is this forward locomotion. This is the same thing that the authors of the paper got. What they did more was improving this velocity. The paper also gives this improvement of velocity. And let's talk about this improvement now. So the reward function was a linear combination of intuitive rewards. For example, yaw. This is a measure of deviation from the straight movement. Was incorporated in this reward function, and as we see throughout the training, the yaw was firstly changing, like the robot was turning, and we also observed it in the real experiment. And after some training, it learned how to move straight. The velocity reward was based on, in simulation, it was based on the output given by the simulation, but in the real world, we had to rely on intrinsic parameters. So our estimator was based on Kalman filter on joint angles and joint angle velocities and foot forces on the floor. And this is a known approach to measure velocity. However, it turned out that it's not as informative as we need to in such small range of motion. So the authors of the paper used the depth camera which we lacked, the depth camera which had incorporated the measurement of the velocity in itself. So clearly, improving this estimator is a key direction for future work.
Okay, so after observing the robot's behavior on the floor in No Magic Lab, where there was high friction, we seen that the robot's exploration was insufficient to learn to walk. That's why we reviewed the setup presented in the original paper, which also supported this hypothesis. We changed friction parameters in the simulation, and the robot indeed struggled to walk. It frequently failed and was only able to learn short forward movements. That's why we decided to reduce the friction in the real world setup to better train it. Here are some metrics from training in simulation. And as we can see, the robot only is able to learn to walk where the friction is low. But we had other challenges in the APRL. First thing was that we used different robot version, which has different weight and strength. And therefore, we had to tune PD controller parameters and torque limits on joints to adapt it to this robot's natural parameters. And the biggest challenge that we had was the research quality, the research repository quality. And we have to sift through a lot of parameters to tune it. And now let's talk about the second approach, which is domain randomization Eureka. And in this approach, we first had to set up Isaac Gym, which is now no longer supported environment and lacks documentation. Then we had to adapt the algorithm for the new version of the robot. We managed to successfully train it in simulation on both robot models, and this is thanks to modifying simulation engine parameters, which decreased the video RAM usage per sample and allowed for parallel samples to run. To show you the scale of the training in domain randomization Eureka, the algorithm consists of 5 iterations, each one with up to 16 samples running in parallel, and each one uses 9 gigabytes of video RAM, which would result in peak almost 150 gigabytes of video RAM usage. If we would run it in sequentially, the algorithm would take 18 hours. After our modifications, the training was optimized for only 20 hours.
All right. During our experiments, we've managed to successfully train both robot models in the simulation for the task of forward locomotion. As we can see on the video recordings, the learned policies are stable and both robots attain their target velocities. So here we have some more videos. as you can see, out of 7 iterations, after 7 iterations with 16 samples per iteration, with 15 final reward functions being correct Python codes, only one out of the corresponding policies is a stable policy that performs the task, despite other policies converging as well to some local minimals, but we can see that those are clearly not suitable for a real-life deployment for obvious reasons. All right, here are some numerical evidences that the learned policy is correct, and conclusions. Although we didn't have enough time to implement domain randomization, which is essential for sim-to-real transfer of the algorithm, as a result, even though we have a successfully trained movement, it is not safe to deploy it. However, we invested significant effort in preparing the simulation and tuning training parameters of the training to finally obtain a successful policy of this LLM-based algorithm.
Okay, thank you very much. That's all we did. Okay.
So I'm super interested if there is like no optimal strategy for this walk or roll that you can see if you can, or there are tasks where you know the optimal strategy for some action.
Optimal strategy for moving forward.
For example.
We had a lot of intuition looking for the movement that we wanted to see. As Maciek showed us in Dr. Eureka, those algorithms were moving forward. However, we were looking for something that was
Yeah, but I think the answer is that it depends on the specific conditions, because as we've seen during the presentation, it depends on the friction parameter, it depends on the shape of the surface, it depends on many real-world parameters. So I would say that there is no like one single optimal solution. There are in fact multiple correct optimal solutions.
What we can see in the APRL simulation, the robot to learn to walk forward is actually a bit sliding on the
it's exploring low friction.
back legs. That's why it wasn't able to learn in high friction environment.
So is there a way, I assume that it has some sensors, right? So it can kind of infer the friction parameter, for example.
Those are force sensors on the floor.
Yeah, I think it would be a rather hard task to infer the friction parameters.
That really is cool. Thank you.
Thank you.
Thank you.